All right, there's 24 and a few others. So if you need to see any of those that are showing, take a good look.
I don't remember what I did. Right.
Remember at this point what we're able to do. We're able to take the derivative of a constant. We're able to take the derivative of x. We're able to take the derivative of using the power rule and the combination, well, using the combination rule, we're able to take the derivative of any term, x term with an exponent on it. We can take the derivative of sine, we can take the derivative of cosine. But there's a lot of stuff we can't do. We cannot take the derivative of two things multiplied together unless one of them's a constant. We cannot take the derivative of one thing divided by another unless one of them's a constant. Okay? So there's a lot of things we cannot do. Joseph, question? Which number are you looking at? Okay? Yeah.
On 29, for the first step, did you basically just do square root of x over square root of x times square root of x and then cancel out the square root of x's? Did you do it that way? And end up with
Yeah.
no square root of x?
Yep.
That makes sense.
All right, what else you need to see? We're okay with the stuff that's showing here? Okay, what else? 43, or the 31. 31? Okay, remind me, we'll do 43 next. There's 31. Now on this one, let's see, what are the directions for 31? Find the slope of the graph at the given point. So we rewrite the 3 over x squared to be 3x to the negative 2, use the combination rule, try to put it back to make their answer look like the problem did. So once we found the derivative, we're not finished on this one. We're supposed to find the slope of the graph at the point 1, 3. So use your derivative as a formula, like we did all in the previous section. Well, in fact, like we've done ever since we learned that a derivative was an actual mathematical thing, okay? We've used it as a formula to find the slope of the tangent line, or to find the rate of change, or to find the velocity of a moving object. We haven't really done the other two yet, have we? But anyway, that's what they are. So f prime of 1 becomes negative 6 over 1 cubed. And we get negative 6. 31 makes sense? All right, let's look at 43. All right, on 43, you got to do something that you've forgotten you're able to do, which is to treat a division problem as a division problem. Because we always say x cubed minus 3x squared plus 4 over x squared. That's what we say. But what does over really mean? It means divided by. So I did the division. X cubed divided by x squared is x. Negative 3x squared divided by x squared is negative 3. And then 4 divided by x squared, instead of writing it as 4 divided by x squared, write it as 4x to the negative 2. And now I know how to find the derivative of each one of those terms. I have a rule for every one of them. So f prime of x equals, well, the derivative of x is 1, because that's a special case of our power rule. The derivative of negative 3 is 0, because the derivative of a constant is 0. And then we use the combination rule to find the derivative of 4x to the negative 2. It's exponent times coefficient, so negative 2 times 4 is negative 8, x, and then subtract 1 from the old exponent. So negative 2 minus 1 is negative 3. Can you get that far with me now? And then the rest of it, we kind of struggle, right? We don't like to leave negative exponents unless we absolutely have to. So that negative 8x to the negative 3, I'm going to make that negative 8 over x cubed. And I'm actually kind of happy to get that far, but I also remember that I'm supposed to try to make my answer look like my problem if I can. So what I did next is that 1, well, anything divided by itself is 1. So I made that 1 x cubed over x cubed, and then I just added the fractions together. I combined the numerators over the common denominator to get x cubed minus 8 over x cubed. Now, I'm going to be pretty lenient on how much, I started to say simplify, but that's not even really the correct word, on how much rewriting you do to your answer for now. Once we start doing what are called optimization problems, where we find maximums and minimums, at that point, we'll have to write our derivative like that. We'll have to. We won't be able to work the problem otherwise. Okay? But I don't want you to get so hung up on that now that you don't learn the calculus. Okay? So I'd like for you to be able to get to what I circled, and eventually we'll have to be able to get to what I circled, but, you know, we can take it in stages. All right? Does that help for 43? Well, now you know what to do for 44, don't you? Same kind of thing. 2x squared divided by x is 2x. Negative 3x divided by x is negative 3. And 1 divided by x you can write as x to the negative 1. Then the derivative of 2x is 2. That's the combination rule, all right? You've got 2x. You take its derivative. So exponent of 1 times coefficient, that's 2. Subtract 1 from the old exponent. Well, x to the 0 is 1. 2 times 1 is 2. Okay, so that's really, in fact, remember it this way if you want. The derivative, anytime you have simply something x, coefficient x, no other exponents, the derivative is always the coefficient. Okay? That's not really a rule, but I mean, you can make it one if you want, because that's the way it always works. Okay? And then the derivative of negative 3 is 0. The derivative of x to the negative 1, that's a power rule or a combination rule. So negative 1 times the coefficient of 1. So negative 1 times 1 is negative 1. X, subtract 1 from the exponent. That's how you get an exponent of negative 2. You don't like to leave the negative exponent in your answer, so that gets you that far. This one, it's a little tougher to see how to get it into one big rational expression. That 2, multiply it by x squared over x squared so that it has the same denominator as your negative 1 over x squared, then you're in business. Okay? You with me on 44? All right, what would you like to see next? 50. Yeah, notice on 50, I got lazy too and decided not to turn that into one rational expression because I didn't want to do all the multiplying. In a few sections, I'll have to do it. But I didn't today, so I didn't. Quick, off the top of your head, what's the derivative of the sine of x? Cosine of x. What's the derivative of cosine of x? Negative sine of x. Good. Pick one. They've all been so far. All right, on 14, we got y equals t squared plus 2t minus 3. So the derivative of that, using whatever notation you want, I use dy dx, would be derivative of t squared. Use the power rule. That would be 2t to the 1, or 2t. The derivative of 2t, using the combination rule, would be 2t to the 0, but t to the 0 is 1. 2 times 1 is 2. And then the derivative of negative 3 is 0. So that's how we get dy dx. Actually, it should be dy dt, shouldn't it? dy dt equals 2t plus 2. Do you know why it should be dy dt, not dy dx? Yeah, dy dx means that the variable's x, so it's dy dt. Yes? You could write y prime. Yeah. Like I did on 16, I used y prime. I just tried to use a few different things. All right. So does that answer your question? All right, what else? We will in just a second. We good? Hooray. All right, now let's take a look at the homework we haven't covered from section 2.1. So what questions do you have from 2.1? 49. And on 49, the directions say that the limit represents f prime of c for a function f and a number c. Find f and c. So what we're given is this. We're given as the problem the limit as delta x approaches 0 of 5 minus 3 times the quantity, 1 plus delta x, and then close all that quantity up, minus 2 over delta x. Now, there are two different forms of the derivative that we have that has the c in there. Okay? One is actually what we called the definition, or what the book called the definition of the slope of the tangent line. Okay? The other that I used in a couple of other problems was the alternative form. So the first thing I'm going to try to decide is which form does this look like? Does it look like the derivative, or the definition of the slope of the tangent line, or does it look like the alternative form of the derivative? Well, 49 looks like that to me. Okay? You tell me. I was about to ask, what am I looking at to see the difference? Well, yeah, the delta x. With the delta x in the bottom, as opposed to something like on 51 and x minus 6, I'm going with the one that has the delta x in the denominator. Okay? So I'm going to try to figure out then, so what I think I know is I think that what I have circled in red is a specific form of the general definition I have circled in blue. Okay, that's what I think's going on. Well, let's see if I can make it work. So what would the f of x be? Well, remember how f of c plus delta x has to work. You go back to your original function f, and everywhere you see an x, you put in a c plus delta x. So that's what I think is in that bracket right there. Okay? So I see one place where there's a c plus delta x. Right here. So I'm thinking c must be 1, right? I think c must be 1 since it's a 1 plus delta x instead of a c plus delta x. So I think c must be 1. Now, the c plus delta x replaced x. So if I see 5 minus 3 times c plus delta x, that's 5 minus 3 times x. You with me? So that's how come that's f of x. And I had already decided that c must be 1 when I saw 1 plus delta x. So that's how I figure out what f has to equal and what c has to equal. If you're not convinced that this is true, I think f of x is 5 minus 3x. I think c is 1, Well, let's compare it. F of c is 2, isn't it? Let's see if it really is. F of 1 would be 5 minus 3 times 1. It really is 2. So now I'm pretty convinced I'm right. Because if the f of c hadn't worked out, then I think, uh-oh, I got something wrong. But the f of c worked out to be what I wanted it to be, so I'm feeling kind of confident about that. Not kind of confident, I'm feeling confident about that. Can you actually feel kind of confident? Or is kind of confident actually not confident? On the brink of being confident. Huh. Yeah. So I'm probably certain.
So you're not certain. I'm 99% sure.
Yeah, I forgot about that commercial. All right. How'd you do on 51 and 52? I used the alternative form on those. See if they make sense to you.
Oh, yeah.
When they're in the alternative form, it's a little easier to pick out. I mean, because the f of x is somewhat obvious. Uh-huh. All right, it's just x minus c, x minus 9, c is 9. All righty. 41 and 42. Let's take a look at 41. The directions say, or the question says, the tangent line to the graph of y equals g of x at the point 5, 2 passes through the point 9, 0. Find g of 5 and g prime of 5. All right, so they're telling us that the point 5, 2 is on the graph of g. So that means, here's where you just have to understand what how notations work, what a notation's telling you. If 5, 2 is a point on the graph, that means whenever x equals 5, y equals 2. Saying that g of 5 equals 2 is another way of saying that whenever x equals 5, y equals 2. Okay? Now, they tell us that the tangent line that from that point goes through the point 9, 0. Okay, so I know that this point is on the tangent line. They told me. I know that 9, 0 is on the tangent line. They told me. Well, if I have 2 points, can't I find the slope of the tangent line? Therefore, slope of the tangent line equals y2 minus y1, 0 minus 2, over x2 minus x1, 9 minus 5. So I get negative 2/4, negative 1/2. Is that all I had to do? All right, yeah, because I found g of 5. It was 2. Then I'm supposed to find g prime of 5. Well, when I find the slope of the tangent line, what is the slope of the tangent line? Derivative. We usually say it the other way around, right? We say the derivative is the slope of the tangent line. But the slope of the tangent line is negative 1/2. That means the derivative is negative 1/2. So the derivative at that point. And look, that's what this notation means, isn't it? The derivative when x equals 5. So we found g of 5 just with the information they told us. We figured out what it meant. And then we found g prime of 5 because that's what the derivative equals when x equals 5. Make sense? All right, 42. The tangent line to the graph of y equals h of x at the point negative 1, 4 passes through the point 3, 6. Find h of negative 1 and h prime of negative 1. All right, so since the point negative 1, 4 is on the graph, that means that whenever x equals negative 1, y equals 4, the notation we can use for saying that is h of negative 1 equals 4. So we found the first thing they told us to find, h of negative 1. With me? All right. The tangent line at the point negative 1, 4 also goes through the point 3, 6. So we can find the slope of the tangent line using the slope formula. That gets us here. Now, since the tangent line, maybe I should say it this way. Since the point of tangency is negative 1, 4, that means we're finding the slope of the tangent line is the derivative. So that means we're finding the derivative when x equals negative 1. What's the notation to mean derivative when x equals negative 1? H prime of negative 1. So all we got to do is finish the slope formula, and we have found h prime of negative 1. Questions like this are kind of tough, but also really, if you can get these, you understand what's going on. Okay? There's kind of two parts to calculus. There's understanding the calculus and then being able to get the right answer. One thing the AP program does that I like is they will ask you questions about your understanding of the calculus. What's our biggest problem we tend to run into? It's the algebra and the rewriting and all, right? There isn't any on these two. So this is more of an understanding problem. Now, the bad thing about an understanding problem is you have to really understand it. Okay? But they will ask you both kinds of questions, a ton of both kinds. We tend to do, by the end of the year, you'll get pretty good at coming up with the right answer. You'll be able to work these page-long problems and get the right answer. Because we'll practice them enough, we'll do them over and over and over and over. You'll get good at it. But you got to understand what's going on, too. And a lot of times that's the toughest part. Because we always like to think, oh, once we have understanding, then we'll be able to work the problem. Sometimes it kind of works the opposite way, doesn't it? You can imitate what I'm doing, even if you don't understand what I'm doing. And we get good. You guys are smart. You get good at imitating. Okay? And that's a good thing, because you're getting the right answers. But questions like this ask you if you really do understand it. And some of you do, and some of you don't. And sometimes you do, and sometimes you don't. But we got to work on always understanding what's going on. This one's as much a notation issue as it is anything else. Do you know what that actually means? It means the value of the derivative when x equals negative 1. Okay? All right, what else? All right. All right, on 47, it says sketch a graph of a function whose derivative is always negative. All right, well, I kind of cheated. We know how we've determined that the slope of a tangent line can always also be called the slope of the graph. So if the slope of the graph is negative, then the slope of the tangent line is negative, and the derivative is negative. So I just drew a line with a negative slope. Okay? As long as I draw a function that's always decreasing. It's not a line anymore, it's a curve. If I draw a tangent line right there, its slope is negative. If I draw a tangent line right there, its slope is negative. Right there, its slope is negative. Or even if I did this, what if I drew a graph like this that's always decreasing? Slope of that tangent line is negative. Slope of that tangent line is negative. Slope of that tangent line is negative. As long as the graph is always decreasing, its derivative will always be negative. Make sense? Then on 48, they want us to sketch a graph of a function whose derivative is always positive. So again, I kind of cheated and just drew a line with a positive slope. But guess what else I could have drawn? A curve that's always what? Always going up to the right, always increasing. Look, if that's my curve, the slope of that tangent line is positive. The slope of that one's positive. The slope of that one's positive. Or, let's see if I can do this right. I always have trouble drawing one that's concave down, but have to think about it for a minute. What if it looks like that? Slope's positive, slope's positive, slope's positive. As long as the function is increasing, the slope of the tangent's positive, the derivative's positive. Oh, you know what I just did? I just snuck in the first derivative test on you. Ooh, there I go. Ooh. Yeah. We'll call that the first derivative test later on. When we get to the first derivative test, everybody remember that we just now did it. Make a note, write it down somewhere. On September 12th at 9:32 a.m., we just talked about the first derivative test. All right, what else would you like to go over? Anything else from 2.1 or 2.2? 59. Ooh. All right, let's take a look at this one. The figure shows the graph of G prime. So that's not the graph of G, that's the graph of G prime. A wants to know what G prime of 0 equals. Well, if that was the graph of F and they ask you for G of 0, wouldn't you just find the y coordinate when x equals 0? So it's the graph of G prime, and they want to know G prime of 0. So shouldn't you just find the y coordinate when x equals 0? So that's how we get G prime of 0 to be -3. Then they want us to find G prime of 3. Well, there's that point. Its y coordinate is 0. Part C. What can you conclude about the graph of G knowing that G prime of 1 equals -8/3? All right, if the derivative is negative, what did we just say about the function? It's decreasing, right? When I drew those with functions that were decreasing, the slopes were negative. So if the derivative is negative, the graph must be decreasing. So since G prime of 1 is negative, because, well, you can see it on the graph, and they told us it was -8/3, then G itself, since the derivative is negative, then G itself has a negative slope, right? Derivative is slope, so G itself has a negative slope. And if G itself has a negative slope, G itself is decreasing. Yes? Now, this is good stuff. This is stuff you need to understand. All right, let's look at D. What can you conclude about the graph of G, knowing that G prime of -4 is a +7/3? So let's be thinking here. Increasing functions and positive derivatives go together. So wherever the derivative is positive, the function itself is increasing. So if the derivative is positive, that means the function itself has a positive slope, and if the function has a positive slope, it's increasing. And notice that when I write it up, I'm talking about the specific point they tell me. But in general, negative derivative and decreasing function go together, always. In general, positive derivative and increasing function go together, always. Okay? E. Is G of 6 minus G of 4 positive or negative? All right. since G prime of, wait a minute. Since G prime is positive at 4, 6, because how did I get 4, 6? Let me think a minute. Oh, okay, that's the interval. Okay. Since G prime is positive on the interval from 4 to 6, how do I know G prime is positive on the interval from 4 to 6? Because there would be 4, there would be 6. So the derivative is positive on that entire interval. If the derivative is positive on that entire interval, that means the graph itself has a positive slope on that entire interval, which means the graph itself is increasing on that entire interval. And if the graph is increasing, think about it. Up to the right, wouldn't the value there minus the value there be positive? Did you follow all that? All right, and then finally, F. Is it possible to find G of 2 from the graph? No. What we do know is that G has a negative slope when x equals 2. How do I know G has a negative slope when x equals 2? Yeah, because G prime of 2 is right about there, and that's a negative y value. All right? So we know that since G prime of 2 is negative, but that doesn't mean we know what the actual value at G of 2 is. You will find as we go through the year, a lot of times we don't need to know the actual value on the graph to know what we need to know, to learn something about it and use it. Okay? Whew, that was a tough one. Who assigned you that one? Yeah, some crazy person. If you can understand 59 mostly, then you understand what you need to understand at this point. Okay? Not that you understood it when you did it the other night, that you understand it now. And if you don't, then I need you to go back, and what were the other ones? 47, 48, and 59. If those don't make some sense to you, go back and try those again. Okay? Because it's kind of a sneak preview. I haven't taught you this yet. And I'm gonna. Okay? We're going to have a big formal lesson over just that stuff. But if it can make sense to you now, then you're in good shape. So if it doesn't, go back and do 47, 48, and 59 again. And if it does, then all right. Okay?